Let's take a look at your activity 20, your chromatography of your amino acids. Okay, and so this one, your chromatography, and so accordingly it was originally applied to separate colored substances, and so like in your colored inks. No, and so but then with a simple technique, and so this one can also be used to separate colorless substances like your amino acids, and then they can be separated, and then you can visualize the separation after you stain them. Okay, and so this one, your chromatography involves a sample or your analyte that is being tested. And so this a sample or analyte is dissolved and so in a mobile phase. And so that is either be a gas or a liquid or a supercritical fluid. And so your mobile phase here is a fluid. Okay, and so the mobile phase is forced through an immobile or your stationary phase. No, and so they are they say the phases are chosen that such that accordingly the components of the sample have differing solubilities in each phase. No, and so the interactions between the say mobile and immobile phase. No, and so a component accordingly. And so this one, a component which is quite soluble in the stationary phase uh, will take a longer time to travel through it than a component which is not very soluble in the stationary phase. No, and so but very soluble in the mobile phase. Okay, and so you have there, and so as the result of what they call this, the interactions, and so the interactions between the two, and so this difference in mobilities, and so your sample components can be uh, separated from each other as they travel through the immobile phase. Okay, and so you have there, and so let's take a look at your activity 20, your chromatography of your amino acids. So this one, your chromatography is a separation technique. Okay, and so this is a separation technique, and so that is again your chromatography is a separation technique, and what they call this, a technique that is utilized for also analyzing the mixtures so into their individual components. No, and so with your principle of your chromatography accordingly, that is based on the differential distribution of components between a stationary phase and a mobile phase. Still, you have here the interactions of the sample in your stationary and your mobile phase. Okay, and so you have compounds interact differently with your mobile and stationary phase, enabling the separation. Okay, and so you have there. And so let's take a look at the one. Okay, and so your mobile phase, and so that is a fluid that moves over the stationary phase. And so as what we said earlier, and so that is either a liquid or a gas. And so and this one accordingly, and so your the choice of a mobile phase, and so also depend on the type of chromatography and the nature of the compounds being separated. And so in your chromatography you have actually a lot of types of chromatography. And so but then for this particular experiment, and so we utilized your paper chromatography. And so the paper being the immobile phase or the stationary phase, and what we use in the laboratory for the mobile phase? Yes, we have your butanol ethanoic acid mixture. No, and so it is a somewhat, yeah, it's a gas. No, and so it is volatile, but then it's still a liquid. No, it's not a gas, but then it's a liquid. Okay, and so your butanol ethanoic acid mixture. Okay, and so as what I've said earlier, you have a lot of type of your chromatography. No, and so you have your thin layer, you have your other types of chromatography. You have your adsorption, your illusion chromatography. You have a lot actually. Okay, and so but then for us, what we use in the laboratory actually is your the mobile phase again is your butanol ethanoic acid mixture. Okay, and then you have your stationary phase. Your stationary phase here, and so that is the immobile. And so the immobile one, and so this one is fixed in place. Okay, and so this is either a solid or accordingly liquid phase that is immobilized and fixed in place. And so, but then we used your immobile phase is your uh, What man filter paper? That is, yes, your filter paper, no? And so that is made up of your cellulose. Okay, and so you have there, okay, and so again, and so it depends, your stationary phase depends on the type of chromatography being used and the properties of your compounds that you are that you are trying to separate, sorry. And so that is again, and so your chromatography relies on the separation of your analyte between separation of your analyte between the stationary phase and the mobile phase. And so your analyte, this is your substance that is being analyzed. In case for us in the when we did perform this one, and so the analytes that we use are actually your five amino acids. No, and so you have your five amino acids with you. Okay, and so in paper chromatography again, and so we use your stationary phase as your cellulose. So I mean your filter paper, and this filter paper, this one is made up of uh, majority of is made up of cellulose fibers. Okay, and this of course the liquid, your mobile phase, and so will move through the filter paper, and your compounds also will move with them. And so that is based on the affinity, for the paper and the solvent. Okay, and so you have here your compounds with stronger affinity. This one is for your separation, and so in your separation of your compounds, and so your compounds with a stronger affinity for the stationary phase will move more slowly. And so because they have a stronger affinity with your stationary phase, no? And then while your compounds with stronger affinity to the mobile phase, and so will move faster. Okay, and so you have there, and then of course giving you a retention time. No, and so giving you a retention time. Of course, at a span of time, at the time that you set actually for us, you have actually 1 hour for that. And so the time, and so your retention time here, and so accordingly the time that it takes for compound to travel through the chromatographic system. And so that is from your injection, and so from what you call this point of origin to the detection. Okay, and so you have there, but then you have for you have here, let's take a look later at your uh retention factor. Okay, and so and you have here it is not actually affected by time or for your retention factor, because and so that is uniform at 1 hour. Okay, and so let's take a look at that. Okay, and so yes, of course, after the separation, and so we're going to detect your analytes. Okay, and so your analytes. Okay, and so after, of course, what we did in the laboratory is we let it dry, let the filter paper dry. Yes, you check your uh, the solvent front, ayan, and the distance that is traveled by your uh, solvent, and the distance that is traveled by your uh, sample, by the analyte. Okay, and so after you separated, you dry, and then you visualize, no, and so you visualize your the separation by accordingly you have what we did is actually your stain, we stained it with ninhydrine. Okay, and so we stained it with ninhydrine. Okay, and so you have here your others, you have your ultraviolet absorption, your fluorescence, and your mass spectrometry, and actually you have others accordingly. Okay, and so but then for that, we stain it with ninhydrine. Your amino acids are stained with ninhydrine. And kapag nag-purple yon, then that is your amino acid, no? And so, but then note that as what I've said earlier in the previous post-lab discussion of this, your ninhydrine, and so is used in forensics, no? And so in identification, I mean, in what you call this, identification of fingerprints, and so, but then, and so you have actually a caution in your uh what you call this in the caution in your procedure, and so that you should wear gloves, no, and so you have there, but then and so moving on, you have your chromatogram, and so your chromatogram, this is a graphical representation of the separation, no, and so separation of your samples, but then and so you have yes, you have the chromatogram. Okay, and so you have there. Okay, and so let's move on. And so this one is actually a setup. And so you have for a paper chromatography, this one is your paper. You have your stationary phase, and then this is your filter paper. Probably we use your filter paper for this. And then you have your solvent, that is your butanol ethanoic acid, butanol ethanoic mixture. And then that is your mobile phase. Okay, and so that is actually your point of origin, your start line. And then this one is your sample. Okay, and so mixture, sabi niya dito. But then, and so we use actually a mixture. Yes, your sample. What your sample here is a mixture of a solution actually of 2%. Yes, your amino acids. Okay, and so your amino is individual amino acids, no? And so you have it as your solvent. But then this one is it should not touch, sabi natin, 'di ba? And so when we did this, the paper should not touch the bottom. And so it should be suspended. Okay, and so let's take a look at the other illustration here. And so this is accordingly the ideal one. Okay, and so it should not touch the bottom of the what they call this, the beaker, no? Ayan, so it should only touch, and so the tip should only be touching uh your mobile face. Okay, and so it should be suspended. And it should not touch. And so, it should not touch. And so, sa atin kasi is we make a cylinder a roll. And so, and it should not touch the walls of the beaker. Okay? And so, this one is a, what you call this, an illustration of a chromatography of your amino acid. Okay, and so you have here at your asparagine. And so, when you stain them, ayan, so ganito yung mga itsura, diba? And so, you have here at your methionine, and so relatively faster. Okay, and so actually this one, it depends actually the movement of this, and so depends also on the R groups. So and so all depends on the R group present in your amino acid. Okay, and so you have your asparagine, your histidine, and so your alanine is relatively it has a relative high affinity with your what they call this, your filter paper, no? Ayan, so hindi siya nag-move ng ganon kalayo, no? And then you have your phenylalanine, your tyrosine, and then you have your proline. Ayan, so your proline, your proline here is not a accordingly, this one will give a negative result for your ninhydrine, and it will give you a yellow color. Your proline and your hydroxyproline will give you actually a yellow color. And so giving you, they are negative for your uh, ninhydrine. But then, for the presentation, ayan, that is for your proline. Okay, moving on. And so this is for your retention factor or your RF value. Okay, and so your RF value is simply a ratio of the distance traveled by your amino acid. And so, of course, from the starting line. And so that is divided by the distance of your solvent front from your starting line. Okay, and so you have there. And so an should be, and so an RF, a retention factor, and so should be should have a value of between 0 and 1. Okay, and so let's take a look at the table later. Okay, and so your RF, this one is your formula for the computation of such, and so your distance traveled by the compound over the distance traveled by the solvent, by your solvent front. Okay, and so this one, distance traveled by your amino acid. And so when you stain this one, ayan, so dun mo na makikita. Okay, and so, and then your distance traveled by the solvent front, right after you remove this, right after you remove it for after the time given, ayan, so you measure your solvent front. Okay, and so let's take a look at your uh, retention factor, your RF values. But then, and so by the way, and so this one, is your your start line accordingly. And so this is your sample. And so when your sample reach here, and so this is the distance. Okay. And so the distance from your point of origin, and so your sample application until this end. And so that is you measure that one. And so examples given here, you have your solvent distance. Sorry, your sample distance is this one is 7.5 centimeter. And then your solvent line is at 10 centimeters. And so that is the distance traveled by your solvent. And so with that, you do your computation. And so your 10, and so 7.5 divided by 10 will give you a 0.75. Okay, and so you have actually, uh, you cancel out, then that is your RF. Okay, and so this one is your, what they call this, your, uh, what they call this, your standard RF value, or your reference RF values for this. And so for your alanine, that is at 0.38. Sabi natin kanina, it should be from between 0 to 1. Okay, and so your alanine, 0.38. Your arginine at 0.20. Your asparagine at 0.5, 0.50. And so aspartate at 0.24, your cysteine at 0.4, 0.40, your glutamine at 0.13, and so and the rest. Okay, and so that is for your reference or your yes, your reference RF values for your amino acids. Let's take a look at the importance of your chromatography in protein analysis. No? And so you have here your chromatography can be used to separate your proteins. No? And so it can be used to separate your proteins, separation of your complex protein mixtures into their individual components based on, of course, their unique properties. No, and so this one is critical in studying and characterizing proteins present in a in a biological sample. No, and so that is for your separations again. And so your chromatography, this one is a technique used to separate, purify, and analyze your proteins. Okay, and so based on their unique properties, and so you have there your R groups with you, no? And so and then your chromatography, this one is used for purifying your proteins from simple mixtures, no? And so you have here your techniques employed in purification. You have your affinity chromatography, ion exchange, and so they are used for obtaining high purity samples, no? And so high purity of protein samples. Okay, and so you have here your uh, chromatography is also used in characterization of proteins, no? And so your chromatography can be coupled with the analytical techniques, no? Like your mass spectrometry. And so examples of this, you have your GCMS or your gas chromatography, mass spectrometry. And so these ones are used in analysis of many chemicals, not only for protein but also for other chemicals, no? And so they are coupled with this to provide a information about the structure of your proteins, no? And so they're important for studying your post-translational modification of your proteins, no? And so the structural features of your proteins also, and the folding patterns. Aside from that, and so as this one is back to your GCMS, no? And so for your gas chromatography mass spectrometry. And so your GCMS, and so this one is the reference method, no? Accordingly, the reference method in drug testing. And so particularly, and so for the detection of your analytes of your drugs of abuse, no? And then you have here, you have your what do you call this? Your protein sequencing. And so your chromatography, this one is uh, uh, part of your important part in your protein sequencing techniques, no? And so you have there, and so this one is utilized to separate and identify amino acid that are released, no? Okay. And also this one, your what do you call this? They are identified in. I mean, they are important in your chromatography is important in protein identification using your proteomics, no? And so and there's also okay. And so you have here also, and so your chromatography, and so also provide and so high sensitivity, no? And so when you say sensitivity, and so that is a when you say a method is sensitive, the method can detect a very low, so a very low amount of protein. I mean a very low amount of sample present in, a very low amount of analyte present in the solution. Okay, and so with this, and so your chromatography is a high sensitive, is a sensitive, and so technique, and so that allows for the detection and quantification of proteins even if they have a low concentrations in a solution, no? And so and they also provide a high resolution, and so that will enable the separation of proteins with similar molecular weights and structure. Okay, and so that is the importance of your chromatography. And your activity 20, your chromatography of amino acids.